Okay. Um, in this particular video, I want to talk just a little bit about basically the importance of water, water balance in the human body. And then I want to spend some more time discussing the basically how we regulate and control water levels in the human body in a separate video. And I apologize, I'm kind of getting over something here. If my voice is a little hoarse or if I cough once in a while, but I have to get this video out for my students, and I've been getting some requests on this anyway, so this will work out perfect. All right. So water balance. So basically, an important part of understanding how we regulate body water levels is just understanding how much water the average person contains. And again, this number is going to vary from book to book to book, but we can say about the average 150-pound person is going to have, give or take, is going to have, give or take, about 40 liters of water contained within their body. Um, and basically, you have to understand how that water is broken up and where you find the varying amounts of water within a person. And basically, we say that water is contained within various body fluid compartments. Okay, and there are two major compartments where we essentially have water, and that would be intracellular fluid and extracellular fluid. Okay, remember, extra meaning outer, outside, intra meaning within. All right. So basically, and then so the where you find the most water in the human body is within intracellular fluid. Basically, remember what that is. That's essentially just the water that's contained within cells. Okay. So about 2/3 of all of our water is located just within the cells of our body. You have to remember we contain trillions upon trillions of, trillions of cells in the human body, and all these little cells, granted they're microscopic in size, they all contain fluid, water within them, and so that all adds up. That's a lot of space to pack water inside of. Okay, and then obviously the remaining 1/3 would be extracellular fluid, or the fluid that is found outside of water. So the bulk of water is found inside of cells, and then the rest of it is found outside of cells in the extracellular compartment. And we can break extracellular fluid down into a few different categories, or there's various areas outside of cells where we tend to find water as well. And plasma would be one of those areas. And remember, the average human has about 3 to 5 liters of plasma within them. And there's a lot of variables that go into that. But so that essentially is circulating water within the body. And then there's what's called interstitial fluid, which is where you're going to find the bulk of the extracellular fluid. That's what IF stands for, interstitial fluid. And remember what interstitial fluid is. That's the fluid that's in the tissue spaces. So let's say if this were a tissue, and then this tissue contains cells. Okay, the interstitial fluid would be the fluid that is contained inside of the tissue but outside of the cells. Or we can say that this is the fluid that cells are bathing in, or bathing within. Okay, so interstitial fluid is the tissue that cells are bathing within. All right, and this is the fluid that essentially, allows for some organization of cells within tissues. This is the fluid where exchanges between blood, between the plasma and the components of plasma and oxygen and carbon dioxide take place between blood and the tissues. So remember, basically, a big part of circulation is just getting oxygen and nutrients into the interstitial fluid spaces of tissues, and then the cells then kind of suck that up and then use it, and then the cells are also eliminating waste across the interstitial fluids into the bloodstream as well, like carbon dioxide and other metabolic waste. Okay, and then there are other forms of extracellular fluid as well that just do not make up much. Overall fluid, there's a lymph, remember we circulate about 100 mils of lymph per hour, cerebral spinal fluid about 500 mils per day, humors of the eye. Now this may be a little bit of new terminology for y'all. Whenever we're talking about human physiology, whenever you see humor, I want you to think body fluid compartment. Body fluid compartment. Okay. So a humor is a body fluid compartment, okay? And the humors of the eye, the vitreous and the aqueous humor, okay? Remember the vitreous humor is in the posterior aspect of the eye where there's that kind of non-replaceable gel, and then the aqueous humor is a constant fluid that's recycled that helps keep the anterior eye clean. Synovial fluid, a fluid that is found within joints. Serous fluids, basically the little bit of fluid that you find surrounding or highly movable organs like the lungs or the heart. There's a little bit of fluid that's in between the heart and the pericardium to reduce friction. Same thing with the lungs. And then some of the GI secretions that take place. I mean, you have to remember that there's always going to be a little bit of fluid kind of within the GI tract that's responsible for carrying various, enzymes or absorbing food and nutrients and so on. Okay, so this essentially is how we break down how much water is within the human body. If you want to take a look at it numerically, um, all right, so that's about how much water is in the body and where you find it. And what's important to understand then is how we maintain this constant, this constant level of water within the body. And basically, body water levels are regulated by osmotic and hydrostatic pressures. Okay, osmotic being, definitely the larger of the two. Okay, remember the hydrostatic pressures. By now, when you're getting to this point in time in anatomy and physiology, you should have gone through the circulatory system, and you should have gained a good understanding of basically capillary fluid dynamics and how fluid essentially, and the fluid cycle of the human body, essentially how fluids are pumped out of the blood and then reabsorbed back into the tissue, and then a little bit, about 10% of that fluid is picked up by the lymphatic system and recirculated back into the bloodstream as well. Okay, but again, the biggest and most quickly influential factor, well, definitely say the biggest factor would be osmotic pressures. Okay, and excuse me. And remember that when it comes to osmosis, remember osmosis is the movement of water across the permeable membrane. Remember, in order for any kind of movement to take place, there has to be some kind of membrane for the exchange to occur. Okay, and obviously the membrane in this situation we're focusing on would be the plasma membrane of cells. All right. And basically maintaining a steady two-way flow of water, across, all areas of the body, but especially around cells, is very important. We want equal amounts going in, and we want equal amounts coming out. Okay, because remember that water levels essentially affect many aspects of the body. I mean, they're going to affect. I mean, again, by now you should have learned about blood and blood volume and all that stuff. And remember that, when you're severely dehydrated, that drops your blood volume down and could cause a decline in blood pressure and cause some other complications. Also, irregularities in body water, are essentially going to lead to unequal amounts moving into and out of cells, and as a result can cause cells to swell or cause them to shrivel up, and either way, both of those are going to have negative consequences on the cell. Okay, so that's one of the most important aspects of maintaining water, normal osmotic pressures, is to ensure, the health of cells, that they maintain their specific shape. Okay, and remember that osmosis is about the movement of water across a um, semi-permeable membrane, and remember that the movement of water is essentially driven by what are called osmotically active particles or molecules. Okay, and essentially ions and proteins are or I should say electrolytes and proteins are the two largest factors that contribute to osmosis and water movement in the human body. So essentially, water balance in the human body is a reflection of electrolyte and protein balance in the human body as well. All right, so let's kind of give a brief little review on osmosis here real quick. I want to, kind of improvising here, but we should definitely just kind of review, give you a crash course in osmosis real quick. So remember, osmosis is all about the movement of water across a semi-permeable membrane. Okay, and osmosis essentially revolves around Okay. Again, maintaining normal concentrations of ions within the human body. So when we're talking about, the tissue spaces of the human body, remember, by now you also should have talked about membrane potentials and action potentials and so on. And remember that there are two major electrolytes that play a pretty key role in cells maintaining a membrane potential or a charge, and that is sodium and potassium. Okay, and remember, sodium is primarily found in extracellular fluid, and potassium is primarily found within intracellular fluid. Okay, and remember, there's a very unequal distribution of these two ions across the cell membrane, and that unequal distribution is primarily created by the sodium-potassium pump. Okay, the sodium potassium pumps of the body. Now, this is something that is frequently taught. Well, I mean, this is something you learn about when you're learning about action potentials and membrane potentials and so on. And the main job, the sodium potassium pump helps the cell maintain this electrical charge, but the real job of this pump is to maintain normal osmotic pressures. Okay, to maintain normal osmotic pressures. Okay, so remember, I mean, by now you know that water is a very polar molecule, that's made up of an oxygen and two small hydrogens. Okay, and one end of the water is very negative, the other end of a water molecule is very positive. Okay, and remember that anything that essentially has a charge, anything that is polar can, essentially mix with water because of this, because of the extreme polarities of water. So as a result, and that's why water is a universal solvent. Okay, and remember that we're talking about attractive type forces here. So you see these two ions that have, that have charges to them. They're going to essentially attract water one direction or another, and that's where the sodium potassium pump comes in, because if we're going to maintain a very extreme or high level of extracellular sodium, that's going to favor a shift, obviously, in water out of the cells. But we counterbalance that by also maintaining a high level of intracellular potassium. Okay, so by maintaining this unequal distribution of these two positively charged and very frequent ions in the human body across cell membranes, that allows for for nice, steady osmotic pressures across the cell membranes, and that allows these cells to maintain their shapes and their functions. Okay, so bear in mind that that's why essentially why that unequal distribution of those two are created. Okay, so then if we get ourselves into a situation where, let's say, we become severely dehydrated. Oops, and I'm kind of jumping ahead a little bit, but again, you guys should have gone over this by now. We're just going to put a lot more application to this. So let's say, and you know that there's always a little bit of sodium inside of cells and a little bit of potassium outside of cells as well. All right, but let's say that the osmolarity, or the overall concentration of sodium, is 300 sodium ions per liter of water within cells. Okay, and let's say a person loses a lot of water and now they become severely dehydrated, and making their extracellular fluid a lot more concentrated with sodium. Well, now what direction is water going to move? It's going to move out of the cell. Okay, it's going to move. Now, this is where people tend to get screwed up, because you always learn about diffusion as the movement of ions across from an area of high concentration to low concentration. Remember, with osmosis, this is not about the movement of ions, it's about the concentration of them across the cell membranes. Okay, and the concentrations of these osmotically active particles or ions are going to influence the movement of water. So remember, think of this again as exerting like a pulling force on water. So if there's a higher amount of ions on one side of the membrane than the other, then that's going to create a pulling force across that cell membrane and bring water out of those cells, which is going to cause them to shrivel up. And then, if we don't correct this, those cells they will start dying. Okay. And then vice versa, if our body water levels, if we become very hypotonic, or hypotonic meaning very dilute. Okay, so let's say, sodium, the osmolarity is 100 sodium ions per liter, and then we're sticking with normal 300 here. Okay, you know that water is going to be drawn into the cell now. Okay, water would be drawn in, and that would cause cells to swell up and then again die as well. And remember, I hate the fact that textbooks talk about it like this. Cells are not balloons. They're not going to pop when they, or burst when they fill with too much water. They're going to die long before, they're going to die before they actually break open like that. Because remember remember cells contain organelles, and that cells essentially are just little assembly line like factories to manufacture proteins that the body and that the cells themselves use. If these parts of the assembly line get pushed too close together, too far away from one another, they're not, the efficiency of that cell and its ability to make proteins are going to be severely hindered. And then as a result, that's going to cause the cell to die. So if we're at this point in time and the cell actually breaks open, okay, that cell's long dead by the time that thing actually breaks open. So that's kind of something to keep in mind about that. So again, hopefully this little review of osmosis helps out, kind of helps you think about this. All right, and bear in mind that I've already kind of started hinting on this, the composition of body fluids. Again, bear in mind that these electrolytes have the largest influence on water movement, within the human body. Okay, and remember that electrolyte essentially is they're essentially minerals that when you mix with water, they dissociate. Okay, and then they allow that fluid to basically become potentially able to carry an electrical charge. And so basically the inorganic salts like sodium, potassium that I just mentioned, some proteins have charges to them, and acids and bases as well. Okay, like for example, you can go to YouTube and watch a pretty cool video actually about, because when we say electrolytes, people always think sodium and potassium, calcium once in a while, sodium and potassium. But remember, a hydrogen ion, okay, will act like this as well. So for example, if you go to YouTube and like I said, you can find this video, it's kind of cool. How to charge an iPod, I think it's called, or where someone shows you kind of how to rig up a way to charge an iPod with the use of a lemon. Okay, and basically how the high concentration of these polar electrolytes within the fluid can create an electrical current enough to slightly charge an iPod. So that's something to kind of keep in mind. It's kind of cool. But again, bear in mind the charge. This is the important part of this: is the charge of these ions are what ultimately influence the movement of water across cell membranes. Okay. So basically, something to keep in mind is that if we have very dramatic shifts in electrolytes within the human body, that's ultimately going to affect our water composition, not only our water composition, but more our water distribution within the human body. Okay. So that's something to keep in mind. And we'll come back to that in a little while, but hopefully that this stuff is starting to stick home, and starting to hit home. Sorry. And then water gain, essentially when it comes to, that we lose and gain water on a day-to-day basis. And there are essentially two major ways that we can gain water. Performed water, basically think of that as water, think of this more or less as water intake. Okay, basically through, food and drink. Okay, ingested fluids. Okay, and which one of the two do you think we get more water from? I mean, that's hopefully a question I shouldn't have to ask, but obviously that we get most of our water from fluids that we drink, and bear in mind that we can get water from fruits, foods as well. I was just going to ask what kind of foods. Most foods that we eat contain water, just some more than others. Obviously, fruits and certain vegetables are going to contain a lot of water within them. And, there's meats that have some water in them, and, some grains have some water in them as well, just not nearly as much. Okay, typically the more processed or cooked the food gets, the less water that you're going to find within that food. Okay, so that is our main route of water gain, is through ingestion. All right, and then we also gain a little bit of water per day through our metabolism, through a process, remember, called dehydration synthesis. Okay, essentially, and the bulk of this, this water comes from carbohydrate metabolism. Okay, remember, dehydration synthesis. Remember when we basically when when we metabolize carbohydrates, and we wind up forming water molecules as a result of this. So basically, remember that carbs are linked together by these glycosidic bonds. Okay, and then when you have the right enzymes and chemical reactions, and we separate these carbohydrates from one another to form monomers or single sugar units, what we wind up with is they wind up getting rid of an OH and an H, and then obviously when you put that all together, you get water. Okay, so through carbohydrate metabolism, we wind up forming a little bit of water, but not much. Only a couple hundred mils of water per day come from overall carbohydrate metabolism. But obviously, there are certain things we can do to our body to possibly increase this. For example, if you exercise and you increase your rate of burning carbs, okay, you may gain a little bit more water through that, but you're also going to lose a lot of water through sweating and so on. Okay, so that's essentially how we gain water. And then when it comes to water loss, okay, the greatest route of water loss is going to be through urine. Okay, through urine. Because by now, you also should have gone through the urinary system. And remember that 25% of cardiac output, okay, all right, that 25% of cardiac output, remember the amount of blood pumped out of the heart per minute goes just to the kidney. So we're talking on average, 1.25 liters of blood, per minute, just circulating to the kidneys. All right, so as a result, and then the kidneys are filtering organs that are going to continuously filter blood, process that filtrate and tubular fluid and so on, and form urine. And remember that we also reabsorb about 98, 99% of that fluid back into our system as well. But whatever we don't reabsorb back into our system, that's water loss. Okay, and you wind up getting about a 1 to 2 liter loss of water per day through the urinary system. Okay, so that's our largest bulk of water loss is through, excuse me, through urination. Fecal matter, basically something to keep in mind, there's always going to be a little bit of water in your feces, but something to keep in mind about the GI tract, whatever you don't absorb, you're going to poop out or defecate out. Okay, that's very technical. So whatever you don't absorb into your bloodstream from your GI tract, you're going to eliminate from the body. Okay, and that's essentially what causes diarrhea. When you have some problem, basically reabsorbing water back into your bloodstream, and a lot of water is reabsorbed back in through the colon. There's a healthy amount of it is absorbed into the small intestine as well. But if you have an infection or anything else going on with your GI tract, okay, and you're running water through it faster than you can absorb it, then that's essentially diarrhea, okay? And then that's going to be a problem because you're not only going to be losing water, you're going to be losing electrolytes as well because you're not absorbing those electrolytes. And that's going to cause severe dehydration, fevers, and all that, increased body temperature and so on. We do lose a little bit of water just through breathing. Okay, the respiratory system, remember the respiratory system is lined with mucous membranes, and there's constantly air moving in and out of those membranes, and then as a result, we lose and gain water based on, essentially based on how humid or how dense the air is with water. Okay, essentially, the more humid the air, the less water we tend to lose. Okay, because the vapor pressure of air is higher. Now, when you're in the winter time, whoa, sorry. I'm using a different smartboard than usual, so bear in mind if my writing's a little goofy. But during the winter time, the vapor pressure, think of this as just the humidity in the air. I mean, depending on how cold it gets, I mean, it could be almost zero. All right, and being that I live up in the upper Midwest, I'm originally from Wisconsin, but I live in Minnesota now. Bear in mind that, I mean, when we get some pretty cold temperatures up here. I mean, anywhere, around 0, 10, 15, 20 below zero. I've seen it as cold as 40 below before. All right, and once you start getting around that zero mark, okay, in terms of temperature, bear in mind that's going to cause water essentially to, and not as water, but molecules in general. Remember, a decrease in temperature is a decrease in molecular motion, and that causes molecules to huddle closer together, and so on. And it's going to cause that with water. So as a result, you're not going to get a lot of, that water is going to stay in the ground, it's going to stay in the snow, and so on. You're not going to have a lot of water evaporating up into the air. So as a result, the humidity is very, very low. That's why, when you exercise or do something outside in the wintertime, even just walking around outside, your mucus, you notice your airways get really dry really fast because you're going to have an increase in water loss because there's just less water in the air, and and as a result, you're going to breathe more out. It's going to dry your mucous membranes out and so on. That's why you have to be careful when exercising. That's why it's very important. If you, like, for example, I ran cross country for all through high school and college, and I ran outside year round, and it's important when it gets extremely cold like that to wear some kind of face gear over your mouth, just because that'll help you kind of retain the humidity and prevent too much of that cold, dry air from getting in. Okay, so expired breath, sweat. Okay, we lose water via sweat, and again, obviously that's highly variable depending on how physically active you are. Okay, and then cutaneous transpiration, just water loss, via skin as well. It's just not very visible water loss. Okay, so those are the main modalities of water loss. And as I already mentioned, that when it comes to water loss, how much water we lose varies greatly depending on what we do throughout the day. Okay, and like as I already mentioned, we can lose a lot of water. I don't know why this stinking thing uploaded like this, but we lose a lot of, if it's very cold and dry, we lose more water via the respiratory system. Okay, if it's warm and humid, your mucous membranes don't dry out. Okay, when it comes to perspiration, okay, the more dry the air is outside, the easier it is to get water off of the body. Another reason why it's important, that if you work out or do anything physical on a really hot, humid day outside, you have to make sure you stay properly hydrated, because if the air is highly saturated with water, remember, a part of getting rid of heat is we circulate blood, we increase blood flow to our sweat glands, and then we filter more plasma out of our blood, and then we excrete that plasma with the heat contained within and onto our skin, i.e. sweat, and then that's great, but now we need that water to get off of our skin to actually get rid of the heat. Okay, and if the air is super saturated with water, and that air can't evaporate or get off our skin very easily, all that heat just kind of blanket your skin, and that could cause you to overheat. So that's why you have to be careful when exercising on really, really muggy days. All right, so that's essentially how we gain and lose water. Now what I want to talk about essentially is, and I don't know why this thing is uploading so goofy like this, basically the regulation of fluid intake. So how do we essentially regulate how much water essentially enters and exits the body? Okay, and basically the main way we regulate this is basically by monitoring sodium. Okay, monitoring extracellular sodium. Okay, why sodium? Because that's the most abundant extracellular electrolyte within the human body. Okay, and and as we're pumping blood to the brain, which essentially is the area that regulates body water levels, basically, so something to keep in mind is that I've already said this once, and I'll repeat myself again, is that electrolyte balance is going to reflect and influence water balance in the human body as well. Okay, so basically the brain sits there and monitors how much sodium levels are in the body. Okay, and basically, the osmolarity, or the sodium concentration, osmolarity is not specific to sodium. Osmolarity is just measuring the amount of particles in the amount of fluid per liter. Okay, and the average human should have about 300 sodium ions per liter of water. Okay, per liter of water. All right. So if we become severely dehydrated, and basically what dehydration is, that's when you have an increase in water loss. Okay, now you're going to have an increase in water loss more quickly than you're going to lose sodium. When you sweat, you see salt build up on your skin and all that, but you're losing water at a quicker rate than sodium. So as a result, what's going to happen to your osmolarity? It's going to rise. Okay, so once your osmolarity starts getting above 300 and such, okay, let's say it rises up to 500. All right, your brain, i.e. the hypothalamus, or the optic nuclei of the hypothalamus, is what is basically where what are called the osmoreceptors of the body are located, and that's what and these osmoreceptors are sensitive to changes in the osmolarity, or essentially the extracellular sodium concentrations of the blood. All right. So remember that if the changes in blood levels of sodium are essentially a reflection of tissue sodium as well. Okay, because you know that we're constantly cycling through blood and tissue fluids all the time. Via the fluid cycle. Okay. So extreme changes in sodium are going to affect us. Okay, and that's what the brain does. And when it comes to thirst, basically when we have a significant drop in water, okay, what we do is we activate thirst mechanisms. Okay, and I'm not going to get into all this right now, just because I'm going to make a separate video on how we hormonally regulate body water levels. But for now, you should just understand what this concept of dehydration. Okay, this is just when we lose water and our extracellular ion concentrations become a lot more concentrated. Okay, and as a result, that is going to affect, again, the osmotic pressures of water between our cells. All right, and that's going to be bad news. Okay, so again, as I've already mentioned, basically, we need to, by regulating water output, we do this by regulating water or sodium levels. A general rule of thumb, I'm going to say this, and you guys should remember this for the rest of your life. Wherever sodium goes, water follows. Or wherever sodium goes, water goes. Okay, so by causing these fluctuations in sodium levels in the body, especially extracellular sodium, that's going to cause fluctuations in basically water concentrations in the human body. All right. So again, a big part of regulating body water levels is by regulating sodium levels in the human body. Okay, so that's something to keep in mind. And like I said, I'll get into the hormonal aspect of this more in another video. Okay. And as I've already kind of started talking about dehydration, so basically this would be a negative fluid balance, or basically think of this as water loss. All right, so basically when we're dehydrated and we're losing water at a faster rate than we can replace it, all right, that's going to lead to bad news. All right, and basically, this water loss can come from, I'd say the most common loss of dehydration is going to be profuse sweating. Okay, the combination of profuse sweating and water deprivation. All right. But there are other causes as well. Hemorrhaging, I mean, that's pretty obvious. If you're losing massive amounts of blood, you're losing massive amounts of water. Okay, because remember that we maintain constant levels of tissue fluids by, again, cycling blood through them. Okay, vomiting. Vomiting. I mean, that's pretty straightforward. If you're vomiting a lot, well, remember, we use the GI tract, the digestive system, to absorb materials that we ingest or consume into our bloodstream. Okay, if you're vomiting more often than not, that's material that's coming right back out of your stomach that you put into it. And and one thing you have to keep in mind about the stomach is is not an organ that's really designed for the absorption process. Okay, that's the small intestine, and so the stomach is essentially designed just to break down whatever we eat into this soupy chyme, this soupy mix called chyme, that makes it easier for the small intestine to chemically break down food and absorb nutrients. And obviously water is going to come in there with that. So if you're vomiting a lot and that material is not even getting into the rest of your GI tract, well, that's water you're not gaining. Okay, and with diarrhea, okay, if you're pumping that water out, the south end as quickly, more quickly than you can absorb it, again, that's going to cause extreme water loss. Okay, diuretics. All right, if people just overdose or have or not necessarily, whether people improperly take diuretics or someone overdoses on diuretics. Remember, a diuretic is essentially a medication that makes you pee a lot more. So as a result, that's going to cause a significant loss in water. And then diabetes mellitus. Remember, you should have gone through the endocrine system by now. Remember your 3 Ps of diabetes: polyuria, polydipsia, polyphagia. polyuria. Remember, poly means, oops, many. Okay, so if you're urinating in excess because you're excreting too much sugar in your urine and you're dragging a lot of water with it, well, you're going to lose a lot of water. All right. But I would definitely say, oh, and then severe burns. I forgot to mention that. Sorry. Bear in mind that the skin is a physical barrier that essentially, prevents. I should say not prevents. Gosh, dang it, not prevents. That retards water loss or hinders water loss. Okay, so as a result, if people have severe burns and you lose this physical barrier that very tightly helps our body to retain water, people can lose up to 5 times the amount of water than they normally would just from losing a lot of skin from severe burns. That's why burn victims, essentially, there's two major considerations when caring for a burn victim. Excuse me, making sure that, keeping their water levels in check and infection control. Okay, and then essentially when people are dehydrated, they see thirst, dry skin, and oliguria. Remember, ligo means, that's a word for scanty or small amounts of urine. Okay, because that again, I'll talk about this in another video. And hormonally, and with the use of the kidneys, we can greatly influence our water output and retention based on how much water we need to retain in the body. Okay, and severe water loss is going to lead to weight loss, hard time regulating body temperature, mental confusion, because typically, again, if you have these osmotic issues with cells, and the cells are losing their shape and function appropriately, or you're just losing a lot of electrolytes through excessive urination or vomiting and diarrhea, that's going to be a problem. Hypovolemic shock, okay, drop in blood pressure, essentially, and again, obviously, all this can cause a loss of electrolytes. Okay, come on, there we go. All right. And then the opposite of this would be another problem with water is what's called hypotonic hydration. Okay, bear in mind that drinking water that does have some minerals or substances in it is good for you. You should not be drinking distilled water as a water source. I know some people do that. If you do it now, please stop, because a lot of people say, well, distilled water is clean and all that jazz, which is, true in a sense. But the problem with this is, water intoxication is more or less just overconsumption or retention of water. Okay. But basically, what was I going to say? Oh, with the distilled water thing, if you're pumping yourself full of distilled water, that essentially is pure water. Okay, and here's a general rule of thumb you should always remember. If it can go in your car, it should not go in your body. Okay, because you put distilled water in the radiator of your car because you put coolant in the radiator to prevent the car, and there's a whole coolant system that prevents the car from overheating. And you use distilled water because if you put tap water in there, and as that water becomes vapor, remember there's a lot of minerals and materials in tap water. You're going to have all these minerals crystallizing in your cooling system, and that's going to that could damage and plug up the system. So that's why you put distilled water in there versus tap water. So like I said, it's just if you can put it in your car, don't put it in your body. Just plain and simple. Okay. Now the problem with this then, so renal insufficiency, basically, you're just taking on way too much water. You're unable to excrete water appropriately, and or excessive water intake. There are some people that just take in too much water at a time, and as a result, you just retain. You could have too much water introduced into your body as well. Okay. Now, when you drink this very diluted or distilled water, lots of cheap beer or whatever it's going to be, you're going to basically get what's called hyponatremia, basically low extracellular sodium levels. This is going to, so essentially think of this as a drop in osmolarity. Okay, because remember, you're introducing all this pure water into your system, and that's going to cause your body fluids to become diluted. All right, so then as a result, what you're going to see then is you're going to see a shift of water from outside of cells to the inside of cells. Okay, and that's going to cause the cells to swell, and then that's going to cause them to essentially burst. So again, bear in mind, if a person is dehydrated, and here's a cell, and again, the osmolarity of the cell is, again, 300 sodium ions per liter. Okay, and then the outside becomes 500. the osmolarity increases, and again, just to review, that's going to cause water to be drawn out, and then the cell's going to shrivel up, and then all the parts of the cell are going to get all clunked together. And then if you don't fix this, if you don't rehydrate yourself, then, well, you're going to see problems. And, I used to see this a lot when I was running. It's kind of stupid because at the college cross-country level, a person should understand how the heck I could see high school. Because, high school kids are supposed to be kind of dumb. It's just part of being in high school is just being stupid and learning about life, and, you get dehydrated. Sometimes you don't drink a lot of water, you forget about it, you just do stupid things, and then hopefully you'll learn your lesson. If you don't, then we call that natural selection. But at the college level, it's just ridiculous when you see people dehydrated, and then you see them kind of laying on the side of the course and all that. But essentially, I would see this all the time, where running races, where people would sweat profusely. Okay, they would sweat profusely, and then they would just dramatically lose water. So then, as a result, that would cause their osmolarity to increase, because remember, when a person is dehydrated, you're losing water at a more rapid rate than you're losing electrolytes. Okay, so as a result, that's gonna cause your extracellular fluids to become very highly concentrated, with sodium, obviously, which causes an increase in osmolarity of your extracellular fluid, which again is going to cause this shift out. Okay, and then so basically, and now obviously the cells that are going to be very greatly affected by this are going to be the neurons. The neurons and the muscles. The electrically active tissues of the body, the excitable tissues of the body, because they rely on these appropriate electrolyte and water levels to function properly. That's why when you see people when they're severely dehydrated, they almost kind of look like they're a little drunk, okay, because they get kind of lethargic, they can't walk in a straight line, very uncoordinated. That because essentially the brain is shutting down, because you're having these electrolyte imbalances, fluids are shifting in directions that there shouldn't be going. There's a very there's a very negative balance of fluids, so basically you have more fluid shifting out than shifting in. All right, which is going to cause again, it's going to cause problems with all your cells, but you're going to see the quickest problems occur with the neurons of the brain. Okay, and then basically with this hypotonic hydration, so let's say we got a cell here. Okay, and then, I don't know, you just decide to drink a couple gallons of distilled water because you're bored or whatever. All right, so again, normal osmolarity, 300. All right, and then let's say the osmolarity dips down to, here in your extracellular fluids, that's going to cause a shift of fluids into the cells, which essentially is in turn going to cause the cell to swell. Okay, and again, the problems are going to be because the organelles now are going to get pushed farther apart, and then again you lose this this assembly line like factory for proteins. Essentially, when you throw a kink in an assembly line, you're going to have a problem with it. Okay. And as a result, if you don't correct this, all right, this is going to be problematic. So you may have to give the person a diuretic, okay, in a situation like this. You may have to infuse them with some, sodium and so on. So that's basically, problems with water balance. I've already talked about all this. Now, fluid excess, one of the, kind of a, and one of the most common problems, some clinical application to all this that comes with an imbalance or in body water levels is something called fluid sequestration, or think of it as fluid accumulation in certain areas of the body. And definitely the most common form of fluid sequestration is going to be edema. Okay, and edema is caused by lots of factors. Could be caused by circulatory issues, electrolyte issues. I mean, there's a lot that goes into edema. All right, but basically, edema is when you accumulate fluids in the interstitial spaces. All right, and when you do this, All right, when you accumulate fluids in the interstitial spaces, remember, so let's say here's a capillary. Remember that cells are usually no more than about 2 of their own diameters away from a capillary, which ensures for a rapid exchange between blood and cells. If you accumulate a bunch of fluid in between in the tissue spaces, that's going to drive cells further away from the blood, essentially, and that's going to make it harder for them to get the oxygen and nutrients they need and eliminate waste, and that's going to cause cells to die. All right, and hematomas, basically, that's when you hemorrhage into tissues, basically a bruise, essentially, which they're not always bad, but that is blood that's not going to return to the circulation because it's going to sit in the tissue spaces. It's going to coagulate and clump, and then you're going to break it down. So that is fluid that is potentially going to be lost. And then pleural effusions. Okay, basically when you accumulate fluids in the lungs, often caused by, you see this a lot in the elderly population who get pneumonia a lot. Basically, it's very common with infections in the lungs, especially infections that don't go away quickly, is you'll see this when you listen to lung sounds. People their lungs are going to sound really watery and so on. Okay, and then with edema, I'll talk about edema more later on, but edema essentially is something, again, that causes a lot of negative effects on somebody when you do accumulate too much water in the system. And edema, again, can be caused by a variety of factors. Basically a protein insufficient diet. Okay, remember I've talked about in another video the role of albumin and osmolarity and with the blood, and if your plasma protein levels drop, your blood volume will drop because all those fluids are going to start accumulating in tissue spaces. Okay, electrolyte problems, kidney problems, circulatory problems. Most often, edema is primarily caused by circulatory issues. Okay, and edema is going to cause swelling. Okay, and in particular, when you accumulate edema via water, that's what we call pitting edema. Very, very rudimentary clinical test for if you want it, because it's important to tell the difference between pitting and non-pitting edema. Sorry. What pitting edema is when you look at your watch, you take your finger and you press. So let's say here's a swelling, and then you take your finger and you press down on an area of the skin where you see swelling. And what you're going to see is this little pit form. All right, and then after a few seconds, it should go back to the swollen state. Okay, because this imbalance in water essentially is going to cause this imbalance in the forces of blood and water and interstitial fluid is going to cause that fluid to basically reaccumulate. That's why essentially when someone does have severe edema, putting a needle in there and draining the fluid isn't going to fix it, because you essentially haven't fixed the imbalance in the forces of basically water and blood pressure and so on. All right, and edema is going to cause a person to accumulate body weight. You see this a lot with people who are in renal failure and going into dialysis clinics. These people, it's sad to see, but they take on lots and lots and lots of water because the kidney, without the kidneys to eliminate all that excess water, it's only going to just build up in their tissue spaces. And then in those folks, you do have to drain that water out because without the kidneys to do it, what else is going to do so? It could cause functional impairment. You see people with, for example, with congestive heart failure, with right heart failure, and they have systemic edema taking place. And as a result, they have all this fluid accumulating in the dependent regions of the body. Remember, dependent regions of the body are areas where gravity is going to take the greatest effect. And basically, those are the lower parts of the limbs, the ankles and the hands and the wrists. Okay, and as a result, if you have all this water building up in the joints, that's going to cause a lot of mechanical impairment. So you see people walk differently with edema. Pain, obviously, from swelling of the tissues, circulatory impairment, and lots of other complications that go with this as well. Okay, so hopefully this video was a good insight for you about just basically water levels in the body, the importance of electrolytes in maintaining body water levels. And in the next one, I want to focus on kind of how we hormonally regulate body water levels, essentially by regulating electrolyte levels. So as they say on the Red Green Show, keep your stick on the ice.